Hi, welcome to AP Physics 1, Unit 7. Again, we're talking about rotation. In this video, we're going to talk about torque, and we keep relating back to linear to rotational equivalent. So torque is the rotational equivalent of force, okay? And so when objects that they're going to rotate, they're going to experience an acceleration, which we'll get into here within a couple of videos. This means that there is a force exerted on the object to begin that rotation. Now, when we apply a force that causes the object to rotate, now we call it there's a torque, okay? And so what we want to do is we apply a force, right, at a distance. So what happens is there's two things that matter for torque calculations. It's going to be directly proportional to the amount of force that is exerted on the object, and then the force, where the force is applied, okay? And we call that application distance the lever arm. And so if this is my axis of rotation, right, and I'm applying a force in whichever direction, again, remember, because you'll see here later, torque is a vector, so we'll have to account for the direction. So counterclockwise, clockwise. Remember, counterclockwise is our positive direction, clockwise is our negative direction. So the lever arm would be the perpendicular distance between the hand and the axis of rotation. So this piece right here is my lever arm. Okay. Now, sometimes they'll do ranking tasks, which you can see here popping up with this, this wrench. So if we want to rank these from greatest torque to least torque, okay, and one thing to note is that these two, F and what we call R, they have to be perpendicular to each other, okay? If they're parallel, there's no torque. If they're at an angle, only the perpendicular piece is creating torque, okay? So if I want to rank all these A through F, okay, what I need to do is and they all have the same magnitude, right? So the force will be all the same magnitude. So remember, torque is a vector, so we have to account for that direction. So note that, so D will give you a positive torque, right, because it'll spin it this way. B will give you a positive torque because it'll spin it counterclockwise. Now, when we get to A, we're looking only at this little piece, right? So it'd be like, if you want to say it's to be the Y component, right, of that force. But again, it'll spin it in the counterclockwise direction. F will be just a small piece, clockwise. E, clockwise, right? And now look at C, right? So C is, we're applying it parallel to that axis of rotation, okay, that lever arm. So what does that mean? C, there'd be no torque, okay? And so the unit be Newton meters. So if I'm going to rank these from greatest torque to least torque, okay, I'm going to say D is going to be greater than B, which is going to be greater than A. So those are my positive torques, right? Which is actually going to be greater than C, even though C has zero torque, right? It's still going to be a greater torque than the ones that cause the negative rotation, right? And then I've got E, right, which is greater than F. Okay, so there they are, ranked in order from greatest torque to least torque. All right, so let's talk about mathematical formula. So the equation for torque is going to be tau. Again, so this is the Greek letter tau. All right, it's the Greek T. So tau equals RF sine theta. Okay, now if you take physics C, you're going to see this written as tau equals R cross F, because these are both vectors. The cross product lets us know that saying righty-tighty, right, lefty-loosey. Okay, because the way we determine it, if I take and I wrap my finger in the direction of the force, right, that means I'm going counterclockwise. I'm going to the left, right? Notice my thumb points up, right? So that means I'm going to loosen that bolt. Now, if I do it the other way, right, notice that my thumb points down, right, which means I'm going to the right, which means I'm going to tighten it down, right? Again, torque is a vector quantity, so counterclockwise is positive, clockwise is negative, right? So one thing that I like to do here is I like the seesaw type questions. So if I have a force right here, all right, where would I need to put that second force or second object to get this to balance? Right, and again, it's going to be from the distance from the center. Okay, well, all we simply say is that the torque that is going to be counterclockwise will equal the torque that is clockwise, and then we just simply solve for R or F, which depends on which one we're looking at. Okay, in fact, that's going to be our example problem. So let's look at an example problem. So here we have an object weighing 120 newtons set on a rigid beam of negligible mass at a distance of 3 meters from the pivot as shown. A vertical force is applied to the other end of the beam 4 meters from the pivot. To keep the beam at rest and horizontal, okay, sorry, I misread that. What is the magnitude F of the force required? Okay, so all we're simply going to do, torque clockwise, or excuse me, counterclockwise is going to equal torque clockwise, because what you're actually doing is saying, okay, the sum of my torques, right, will be equal to 0, right? Because if I have any kind of movement, okay, I'm going to accelerate the object, and then that means I'm going to have unbalanced torques, okay? These are, this is what we call a static equilibrium problem, okay? So now let's do the calculation. So this, on the 120 Newton side, this is what we'll cause the torque, right? This F will cause the torque. 120 Newton will be our counterclockwise. F will be our negative, will be our clockwise torque. And so we would say R, we'll call it RB for block. So RB FB equals R capital F times F, right? And so I'm solving this for F. All I'm going to simply do is divide both sides by RF. Okay, it goes away here, and it's going to say F equals RB FB over RF, right? It's an R. Now I just simply plug in my numbers. So the block is 3 meters away, has a weight of 120 newtons, and then F is going to be applied 4 newtons away. So this is going to be really 3 times 30. So we know we need to apply 90 newtons at 4 meters away to get these to balance. Okay, so this particular section of Unit 7 will focus on what we call rotational dynamics. So this is the start of it, right? So this is kind of like our Newton's first law of rotation kind of piece to include that torque equation. Next, we're going to talk about moment of inertia, which now moment of inertia will be the rotational equivalent of mass. And then we'll put it all together and look at rotational dynamics.